All right, so we finished up last video by talking about complex inner products defined on just the real axis. And in this one, we're going to talk about complex functions defined in the complex plane and inner products with those. So let's draw them like this. So we're going to have what we're interested in is the inner product u, bar v. There's a lot of different notations for it, but that's kind of what I'm going to use. And one way to do that is to take the integral of u v complex conjugate dz, and this is going to be over some typically closed space, right? So I'm just going to do it like that. I think that's probably the wrong notation, so please let me know or don't get mad at me. But basically what you're doing is you've got some function over some closed space, and you're just taking the integral of that function inside there. And so that's how you define this complex inner product, or its a way. You could also do it along some line integral, as opposed to something inside here. But I think in complex integration theory they call it contour integrals. But in any case, that's how we're going to do it right now. So let's do it. So we're going to draw our domain here, and that this is going to be the z-axis or the z-plane, right? You can have z1 as your real and then z2 here. So let's do this, z1 and then z2 kind of. I hope that sort of helps. So then z is equal to z1 plus z2i, right? Okay, and now we're going to say u is equal to u1, and that's a function of z, right? So two components plus u2 z times I, right? Where the individual u's are real valued functions on the complex plane. And then so v is also kind of similar deal. v1 of z plus v2 of z times I, right? So there's a couple ways to view this. Essentially, if you're used to real numbers, these look like vector fields, right? So, I got to stop drawing in the middle of the lines. It's probably annoying. But, so this is basically how that function looks, right? But there's an arrow at every point inside this field. And, I'm sure people already know this, so I don't need to explain it, but so u1 is essentially this real component, right? And then u2 would be this imaginary component. And, for this one, and that would be at what, like negative 2.5, 2, as your domain element. So the domain here is negative 1.5. Yeah, I said 2.5, but this negative 1.5, negative 2. And then so your u1 value there is going to be, just whatever this component is, and then the u2 value is going to be whatever this component is. So let's go ahead and do it over here as well. I almost didn't draw on the lines again. I don't even learn them for my own thing. So we've got it looking like this, right? And these, again, are all over the place. They're all throughout. And let me see if I can get my coloring going early so that way I don't forget to do it. So we've got kind of orange over here, and then let's do blue over here. So V is blue, 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 and then U is orange. Let's do like that, right? Okay. So what's next? So what we're trying to do is evaluate this integral, because that's the inner product we're looking for. And so what we're going to do is at each point we're essentially making some new function, right? U times the conjugate of V, and then we're just integrating that function. And so that's kind of what I'm trying to get at is, each time we're essentially just making this function and then adding it up. And when we had finite dimensions, we were literally adding them, right? So you you take this one times the conjugate of this, and then this one times the conjugate of this, and then you literally add them, right? You get this one, and then you get another one for the second dimension, and then you add those. Whereas in this, you get one for, infinitely many dimensions, and then instead of adding them in the typical sense, you add them by using an integral, right? So that's my air quotes for adding being integration. So that's kind of where that is. So, and then remember here, what we were doing was we're taking a slice, and at each slice you're computing this u times v bar, and that was this. So you get one of these at each slice. But in this case, what we're doing is at each domain element, so at each point, right? So I'm going to draw a little bit bigger of a vector. So let's say at this point, your vector looks like this, right? And that's pretty discontinuous. So sorry, but I'm doing it that way just because it's easier to draw. So now at this point, well, this one's actually already drawn. So now we have u and v. So what we want is u and v bar. And so that's going to be, we're just doing that same procedure, right? We basically do this same procedure, and we're going to get some new variable that looks, that's totally wrong. I guess I don't really have much intuition for what this times this is. They look like they're in about the same direction, so the imaginary component is probably about 0, because the cross product is what gives you the imaginary component, and if they're in the same direction, then your cross product is going to be 0, right? So I'm actually, let's roll with that. So imaginary component is 0, and what's the real component? It's the dot product of this and this. So this one's magnitude looks like it, and they're going in about the same direction, right? So the magnitude of this is 3, magnitude of that is about 1. So the real value is about 3. So this is our vector right here. So if we're going to draw u and v, right? So this is going to be u v bar at -2, -2. We have a function, or our value looks like this. And so, everywhere else along here, you would do the same thing. You would be like, okay, so at this point, I'm grabbing this vector. So at this point, I'm grabbing, whatever vector this looks like. And now at that point, we're going to do the same procedure, and we're going to get some new vector here, right? Just like that. And then what you do is now you, over this same contour that you have, or over this same domain, you're just integrating, that's so bad. You're just integrating all of these new resulting vectors, right? And that is your complex inner product, right? So I think, maybe the lack of accuracy in my drawing probably took a little bit away from it, but that really is as simple as it gets. So all it is just at each point, you're basically creating this function so you can integrate it. And the way to create it is at each point in u and v, you do our same little process here by taking the cross product to get your imaginary value, and the dot product, which is the same as rotating the 1 and taking the cross, and that gives you your real. And you just do that at every point in z, in your z. And then that will give you some new function, and then you just integrate it over the domain that was defined in your inner product. And again, different inner products will have different domains, and they can have weighting functions actually, and they can have all kinds of stuff in here. And that's actually kind of a multilinearity thing that I was kind of thinking about making a video about, because I think it's cool. But yeah, that's basically all